Our lecture for today is a continuation of the lecture we started last time. So we are still in section 2.3, which is titled the Duality Theorem. Okay, remember we learned about how to form the matrix B, which is invertible, and then we use the matrix B inverse, and then we defined what is the cost function for B, right? And then we learned that to obtain the jth column, assuming we are at some table, and to obtain the jth column of the next table, we will write that to be equals what? So do you remember? So it is B inverse AJ, where J is the column, the jth column in the current table, or in the previous table, let me say. Okay. And also we computed ZJ, and ZJ was B inverse, right? ZJ was B inverse, CB transpose times TJ minus CJ, right? And those the ZJ are the entries in the objective row. So we learned all of that, right? Now we will use these to make theorems about the optimal solution of a linear programming problem and relate that to the optimal solution of the dual problem of it. Okay? And we start with the following theorem, which is called weak duality theorem. Okay, let's go. Assume we have the primal problem here. This is the primal problem, and we call it 13 here. And assume x naught is a visible solution to this primal problem. And the dual problem, you know, the primal is maximized, the dual is minimized. C and B are interchange rules, okay? And we introduce a W, so W naught is a solution for the dual problem. Now, we are assuming that we have a solution for the primal problem, which is x naught, and W naught, the solution of a solution of, I said the solution, I mean a solution of the dual problem. That's W naught. And x naught is a solution for the primal. Then, this is what we conclude. Notice this. Simply, it says that the value of the objective function of the dual problem is always greater than, here we go, the value of the objective function of the dual problem is always greater than or equal the value of the objective function of the primal problem. So, and let us say this theorem easily. The value of the dual problem at any solution, the value of the objective function of the dual problem at any solution is always bigger than, greater than or equal the value of the primal problem at any solution. اوكي يعني اذا كان عندنا حل الدول problem كان عندنا optimal solution واوبتيمال solution للبرايمال problem، فقيمه الاوبجكتيف فانكشن عند هذا السوليوشن للدول دائما اكبر من قيمه الاوبجكتيف فانكشن عند السوليوشن بتاع البرايمال problem. اوكي ايش ما كانوا، ايش whatever solution visible, we are talking about a visible not optimal here. Whatever visible solution you get for the dual, it gives you bigger value for the objective function than any other solution you get for the primal. Okay, good. We will use that theorem, so we need to understand it. Now to prove it, now since x naught is visible solution to the primal problem, so x naught achieves the constraints, and since w0 is positive. Now see what happens, what we have done above there. We multiplied both sides here by W naught transpose. So multiply both sides by this, W naught transpose. So we get this part. Okay? Now notice this is a number. So why this quality is happening? Because this is a number. We can write it this way or that way. Like we can write it like W uh, 1 all the way to W say uh, S times B1, B2 to BS. It is the same if we write it this way, B1, B2 all the way to BS times W1, W2 all the way to WS. We still get the same expression, we get the same number, right? So that's why we have this equality. Okay, good. Now, since W0 visible solution to 4, we have W0 satisfy the dual problem. So it must satisfy that to 14. Okay, so A transpose W0 is greater than C. Okay, so we have this in hand. Or if we take the transpose, you know how to take the transpose of this, take the transpose of that, it will become W naught transpose A. This way, which is W naught transpose times A. Okay, this is because we know that if we have any two matrices, multiply them, take the transpose, it is the same to take the transpose of the second and multiply it by the transpose of the first. Okay, so taking the transpose of this side and this side will give us this information here. Okay, now notice what we do here. Multiply now what we do here. Okay, now how we conclude this in here. Okay, so multiply this by x naught and yes. Okay, so if we multiply this by x naught from both sides, so times x naught will still greater than, and these are numbers, right? And this is what we mean here. Okay, and have we reached what we want? Remember, we want to show that we want to show this. Have we reached it by doing so? Huh? Now, using this part here, this equals B transpose W naught. So what we got now, using all that, you can see that we have B transpose W naught is bigger than or equal C transpose X naught. And this is what we wanted. So done, the proof is done. Okay? So the value of the dual problem at any visible solution is bigger than the value of the primary problem at any visible solution. Okay. Now, this theorem is direct conclusion from the one before. So it says if B is a primary problem, if that primary problem has a visible solution to the objective function, but the objective function is unbounded, then the dual problem has no visible solution. Okay, now to see why this is true, we go back to the theorem. The theorem says the value of the dual problem at any solution is bigger than the value of the primary problem at any solution or at all solutions. Now, we are saying here, if the primary problem has a visible solution, but the objective function is unbounded, what that means? It means the primary problem has a solution, say x naught, but the value of the objective function is infinity, is unbounded. Now, the theorem above says that The duality theorem, any solution for the duality theorem, the value of the objective function must be bigger than this, the value of the objective function at the primary problem. But we are saying we have a visible solution for the primary problem for which the objective function is unbounded, is infinity. And the value here is bigger than that. So this is infinity, which means the dual solution does not have, the dual problem does not have a solution. So this is the conclusion. Then the dual problem has no visible solution. Okay? So if a visible solution for the primal gives you an unbounded objective function, then the dual problem has no visible solution. Now we go the opposite. If the dual problem has a visible solution but the objective function is unbounded, then the primal problem has no visible solution. هذا بروح العكس is going conversely, right? ليش? You remember the theorem we learned last time which says the dual of the dual is the original problem. So when you have a primary problem and you have a dual problem, you can look them at from the other side, saying this is my original problem, the dual one. You can take it to consider it to be the original problem. Then take the dual, it gives you the primal one. So you can interchange the rules. So we can say in this theorem 3.5, if one of the problems, either the dual or the primal or the dual, if one of them has a visible solution for which the objective function is unbounded, then the other one does not have a visible solution. Clear? Okay. Good. Now let's go to another theorem. So now we give a condition that a visible solution to the primary problem be an optimal solution. Oh, okay, good. When we learned about the dual problem, we were wondering why we are taking a dual problem. We having a linear programming problem. Why we are taking the dual of it? Because the answer is because using the dual, we can get information about the original problem, and this theorem tells us one of these things. Okay, now it says, assume we have the primal problem here in 13 again, we call it 13. And X note is, no, did I copy the very same here? Okay. Okay, good. No, okay, let's keep going. This is fine. We are doing fine. So X naught is the solution for the visible problem, and assume W naught is a solution for the dual problem, and this is the primal problem. And if, so we are adding something here, and if the values of the objective functions of the primal and the dual at X naught and W naught are equal, then, so this is the conclusion. So we are saying, and if, and then this is the conclusion, then both X naught and W naught are optimal solution for their respective problems, which means X naught is an optimal solution for the primary problem, and W naught is the optimal solution for the dual problem. So what conditions we need? X naught is the solution for the original, W naught is the solution for the dual, but the objective function here and here have the same value at X naught and W naught. Then these solutions, X naught and W naught, are optimal solutions. Okay, so optimal solutions. So let us see how we prove that. To show that X naught is an optimal solution, we will assume that we have another solution, visible x1, and we show that the value of the objective function at X naught is bigger than the value of the function at x1. So suppose x1 is the visible solution to the primary problem. Then what's happening? Now we know from, this is from the last theorem, the weak duality theorem. We know this equality because that one says the value of the objective function of the dual at any visible solution is bigger than the value of the function of the primal at any visible solution. So X naught is such one. So C transpose X1 is the value of the original primal, and W transpose B transpose W naught is the value of the objective function, the dual. So naturally we conclude that. But now the theorem says that, giving us this hypothesis. So we have this quality here. Okay, good. So we are done. Hence, x naught is an optimal solution. The value of the objective function at x1 is less than the value of the objective function at x naught. x1 is any visible solution. Now we do the opposite. We want to show W naught is the optimal solution for the dual problem. It says here, if W1 is any visible solution to the dual problem, then this thing here must be happening. So let me use this color again and take this away. So this thing here is happening. How do we know that? It is also by the above theorem, because we said the dual is the original problem, and we can consider any one of them to be the dual and the other to be the visible. So applying theorem, the last theorem here means we are taking the dual as no, we are not interchanging here. Okay. Oh, okay. We are not interchanging. So we're using theorem 3.4. Again, W is a solution for the dual, so the objective function is bigger than the value of the objective function here is bigger than the value of the objective function for the prime. Okay, good. Okay, and now this information here, this inequality here, is the one given in the hypothesis. So now we got here the value at W naught is bigger than the value, smaller than the value at W1, where W1 is any feasible solution for the dual problem, and therefore W0 is the optimal problem. Remember that the dual here required minimization. So the objective value at W naught is smaller than the objective value at W1. So optimality here means the least value, right? Okay, good. So now I want you to remember this conclusion here. It says if the values of the objective function primal and dual are equal at some solutions x naught and y naught, then these solutions are primal. Okay, and to prove that, we used the theorem before. Okay, good. Anyone has any questions so far? Now let's go to the theorem after that. The duality theorem. Okay, let us read what it says. If either the primal or the dual problem has a visible solution with a finite optimal. So it's talking about either the primal or the dual. If one of them has a visible solution with finite objective value, then the other has a visible solution with the same value. Good. So the other has a visible solution with the same value. So if you know that the primary problem has a visible solution with the finite value for the objective function, finite optimal objective function, if this happens for the primal, then the dual must have the same thing. It must have a visible solution, which is optimal, and the value of the objective function here equals the value of the objective function there. And the opposite. If the dual problem has a visible solution which is optimal, then the primal problem has a visible solution where the objective value here equals the objective value of the dual. We are not saying they are the same solution. No. We are saying both solutions give values for the objective function of their respective problems, and these values are equal. So if one of them has a solution, then the other has a solution, and they agree on the value of the objective function. This is part A. Okay. Part B says what? If 13 and 14 have visible solutions, then for 13 is the primal, 14 is the dual. Okay, then the primal problem has an optimal solution, say x naught. Okay, so part B says if the primal and the dual have solutions, we are saying visible solution. We are not saying optimal now. But this part says if they have visible solutions, then they have optimal solutions. Then the dual problem has optimal solution, say at x naught, and the dual problem has optimal solution also, say at w naught. And what? The values of the objective functions are equal. Okay, so let us prove this theorem. Okay, now converting the primal problem in 13 to canonical form, introducing slack variables, which we call x prime. You know, the slack variable, you call it xn plus 1, xn plus 2, and so on. These together make them a vector. Like the vector x, we know the vector x is our original variable, say from x1, x2 to xn. Okay. And the vector x prime here, we mean the slack variables, which is xn plus 1, xn plus 2, and then till we reach xn plus m or s. So putting these together, when we say the vector x prime in one vector, when we say that in one vector, then we are just gluing these two vectors together and make them one vector, okay? Okay, so after introducing the stack variables, assume we have the x prime, then we have this thing here. And the problem says maximize. This is the problem in standard form, right? Now make it a canonical form, convert it to canonical, sorry. Then the cost vector will be written this way, right? Then our C will be written using C1, C2 to C, and then you complete zeros, right? This is what we mean by saying, okay, this is, we will take this to be C, and then we do that, and then 0. This is what we mean here. And same thing for the matrix A. The matrix A with this identity here, it means our matrix we already have, A11 all the way to A1, 1n, AN1 to AN. And then we have the identity matrix for the slack variable. You remember that? We used to write it this way, assuming we have 4 columns here. Okay, something like that. So you are familiar now with these notations. Okay, so converting to the canonical form, we are writing it using matrix notation. Now, assume we have optimal solution for this primary problem. Now remember part A says if the primary problem has a solution, optimal solution, finite with finite objective, then the dual problem has an optimal solution with a finite objective. So this is what we want to prove. So we have here the primary problem in canonical form, and we are assuming that it has a solution which we call x hat. Okay, now we want to show that the dual problem has a solution. So we will construct that solution, which will be W down here. And to reach that solution, we do the following. Then there is a corresponding invertible matrix. Okay, we know that, we learned it, okay. And we know that the xb hat is given this way. We have seen this before, right? Now, the objective value of the optimal function is that. And we know that the objective value equals the cost function times the solution, xp hat, which is this. So we have seen all these notations before. Now we define this W here this way. It is B inverse transpose multiplied by the cost function, the cost vector CB. So now we got a vector for W. Now we claim that this W is an optimal solution for the dual problem. And the objective value has the same. The value of the objective function for using W is the same as the value of the objective function using x hat. Okay. Now, if we define this, let's keep going. So W transpose equals that. Now we show, this is what I'm saying, we show that W is a visible solution. So first we will show it is a visible solution, then we will show it is an optimal solution. Okay, let's keep going. Now substitute, by substitution we get, substitute where? Z equal WT transpose, which is that, and which is this. Now you know these are numbers, so as I presented above there, W transpose B is the same as B transpose W. It is a number, right? Okay, so we can do this. That's the objective function value for the dual problem, which is this. Now this is the objective value function for the dual problem. Agrees with the objective value of the primary problem. They do agree really. How? Because if we go up there, if we go up where this is what? This is what? It is here. So this is the same as W transpose B. Okay, good. What is W transpose B? Is the objective value of the dual problem. And this is here the objective value of the primary problem. And they are equal. Good. So we proved that part. The objective value has the same. The objective function has the same value. Good. Now, remember that Tj, we wrote Dj equals B inverse Aj, right? But now our matrix here for this A, we have this matrix, right? The one we introduced already. So we will take the vector J of this matrix and multiply it by B inverse, and then we get Tj. And this is what we are saying here, right? And same thing for Zj. We have seen that Zj equal CB transpose times Tj, okay? And now for Tj, just substitute this because this is Tj. Good. And then we get this part. The optimality criterion requires that, remember what these things are. These are the entries in the objective root. We want them all to be non-negative. So once we reach that, then we reach the optimal solution, right? Now, if we prove this is happening for what we have above there, then we have reached the optimal solution. Okay, so but we need to rewrite it. To rewrite this, these are the components in the row. Now, if we take them as vectors, that means Z minus the C's as a vector minus a vector. We want it to be 0. Like this says like Z1 minus C1. Okay? We want it to be positive. And then we say Z2 minus C2 all the way till we reach Zn minus Cn. We want that vector to be positive, which means all the entries are positive. So we write it this way. Okay? But now we have what Z equals, right? So we will replace this Z here with So we will use that, but without the subscript j, because this goes for the j. We want them all, so we'll take it as uh, one piece because the zj is a component, and we want z the whole vector. So we will remove the j, and this is here the same as that. So we got this. So now multiplying the previous equation by and separating partition matrices. So what we need to do is multiplication. So let me clean all that. Now it talks about this part here, and we know it is greater than 0. Now multiply, like, the matrix. I already wrote what is the matrix AI. It has two parts. It is up there, so let me bring it. So let me, oops, what did I do here? Can I move it again? No, this is bad. Okay. So actually, okay, let me write it again here. This is, we want to multiply, the idea, we want to multiply this with the two matrices. I have a matrix A, which is 1, 1, A, 1, N, A, N, 1, A, N, N, and the identity. Say that is this. Okay, we want to multiply this with, say, some matrix B. So what I do, I multiply B with that, okay, and take that part, which is here. So if I multiply B with the part A, B with A, I get this, okay? And we have this to be greater than 0. Let me clean this again. That means we have C B transpose B inverse times A, and let me write this, is greater than or equal. Just I moved C transpose and 0 to the other side, okay? So I moved it to the other side. So when we multiply this matrix here by A, I get this equal to B greater than this part. And this is what we are having here. Okay? Now, again, when I multiply this matrix again with the identity, I get the matrix itself. It will be greater than this part. And this is what I get in here. Okay? Okay. Good. Now, going back, what is this? This thing here, remember? It is W transpose. So this gives us that. So go back. W transpose. Here we go. It is here. So it gives us this, and therefore we get that. And this is again W greater than 0. Okay. This means that using these, W is a visible solution for the dual problem. Okay, so we have proved what we want. Okay, so we have proved it is a visible solution, and it has the same value as the objective function. It gives the same value at the value of the objective function of the primal. Okay, good. So we are done with proof of part A. Now, if we go back to proof part B, it says if the primary problem has a solution, optimal solution X naught, and the dual problem has optimal solution W naught, then the values of the objective functions are equal here. So we want to prove that. And this goes quick. Assume X is a visible solution and W visible solution for the primal and for the dual. Then we know that always the value of the objective function of the dual at W is bigger than the value of the objective function of the primal at C. This is by the very first theorem we have seen. Since the objective function of primal is bounded by WT and the set of visible solution is not empty, then there is a finite optimal solution. Okay, now what it says, this value here is bigger than the objective function of the primal solution at any visible solution. So this is a bound. So any visible solution for the primal, the value of the objective function is less than this bound. So that means there must be an optimal solution. Okay? Which is X naught. Okay? Now by part A, there is a visible solution W naught because part A says if I have optimal solution for the primal, then I have optimal solution for the dual. Now I showed here the primal has optimal solution, which I called X naught. Then part A says, okay, there must be an optimal solution for the dual and call it W naught. And the values equal. And we have seen in theorem 3.6 says that if the values are equal, then the solutions, both solutions are optimal. Okay. Okay, consider the linear programming problem. Now, look what's happening here. This is the linear programming problem, and these are the constraints. And this represents the area of visible solutions. Okay, what's about it? This problem has an unbounded optimal solution. Why it has unbounded optimal solution? For example, if we go in the in the y-axis, okay, keep going in the y-axis, which means x2 is increasing and goes to infinity, and all these points are optimal solutions, which means x2 can go unbounded. So that means z can go unbounded because both of x1 and x2 are positive. So this problem has an unbounded optimal solution. Now, what this means for the dual problem. Now, if we take the dual, it says minimize, and then we will have 6W1, W2. You know how to make the dual. And we have these constraints. Now, graph these constraints. This line is here. This line is in here. And this is the closed half space of this line, and this is the closed half space. And if they intersect, then they will intersect somewhere here. So the area here is not an area of visible solutions because W2 has negative values. So there are no visible solution. Okay? How this applies to the theorems we have learned. The theorem says if one has optimal solution of finite, then the other one has. So if there is for the primal, then there is for the dual. If there is for the dual, then there is for the primal. That means if there is not for the primal, then there is not for the dual. And the opposite. So both of these, the primal and the dual, either have solutions together or they don't have. Now, because the primal here is unbounded, then the dual does not have a visible solution. Okay, so it's not possible to have the primal problem with an optimal solution of finite, but the dual problem does not have an optimal solution. This is not possible. And the opposite also is not possible. Okay, now the next example shows that neither the primal nor its dual have a visible solution. Okay, this is what I just said. If one of them does not have a visible solution, then the other does not have a visible solution. Let's look at it. So this is the primal, maximize this, and these are the constraints. Okay, so apparently there is no visible solution for the primal. Okay, now take the dual and do the same thing. There is no visible solution again. This is not a coincidence. This is not a coincidence. If one of the problem has no visible solution, the other has no visible solution. If the graph of one problem is this way, then the other graph will be the same way. Okay. If one of the problem has an optimal solution but it is unbounded, then the other problem will not have an optimal solution, or will not have either visible solution. Okay. Now we reach the very last theorem. Complementary slackness. If an optimal solution to the primal problem make a constraint into strict inequality, then the corresponding dual variable must be zero. What does that mean? If the constraint is like less than without equality, say the third constraint is 2x1 plus 3x2 less than 5. This is the third constraint. Then in the dual problem, the third variable must be zero, because the third constraint here was strict inequality. Strict means less than without equal, or greater than without equal. And we know moving from primal to dual, constraints corresponds to variable. So when we say the third constraint in the primal, that gives us information about the third variable in the dual. Okay. Now, this theorem states what we have said. For any pair of optimal solutions, to the primal and the dual. So we're assuming we have an optimal solution for the primal, optimal solution for the dual. See what this says. For I equals 1 to m, the product of the ith slack variable for the primal problem and the ith dual variable is 0. Which means this is the ith slack variable, right? X and I plus 1. This is the ith slack variable, right? And the ith dual variable is what? Wi. The product is 0. How come the product of two variables is 0? They are both positive, they are both numbers. That means one of them must be 0, or both. Okay? This is what it says. If the ith slack variable of the primary problem is not 0, then the ith dual variable must be 0. If xn plus I not 0, then wi must be 0. One of them must be 0. Okay? Now, part B says the product of the jth slack variable of the dual. Now we go the opposite way. The dual, and we interchange the dual and the primal. So if the jth slack variable in the dual, we multiply it by the jth variable in the primal, then the result must be 0. So again, if the slack variable of the dual is not 0, then the jth slack variable is not 0, then the jth primal variable must be 0. Okay? You got this? It's about ith slack variable and ith dual. Ith slack in the primal, ith dual in the ith variable in the dual. One of them must be 0. We go both ways. Okay. So what is that good for? We will see. Let us prove the theorem. Add slack variables to the primal problem. So this part is for adding the slack variables. Remember that? The identity, when we say like x4, in here x5 and x6 and equals, right? So we will have zeros like this. So this is the identity multiplied by x prime, the slack variables. Where are the slack variables? Are these. Then for any dual variable W1, W1, and W2, what we get? How we got that? Just multiply this with W transpose, right? Multiply it if you have W transpose. So multiply W transpose with all parts. So then we get that, okay? And how we get this in here? It is taking, these are, all of them are taking the transpose for both sides, which means W transpose AX, take the transpose, will give us what? Will give us X transpose A transpose W. So you change the order and take the transpose, and WTIX prime, take the transpose, will be X prime transpose I is the same here, and WI, and we have this equal WTB, take the transpose, then we get B transpose W, and this is this information. So it is the first equation, but we took the transpose. Okay, remember what we want to show, that either xn plus I is 0 or wi is 0. Okay, so we will, this is what we are saying. It is either this 0 or that 0, this 0 or that 0. So the multiplication with this and the multiplication with that 0. So we want here, actually, we want what? We want W transpose X prime equals 0. If we show that, then we are done. Because when we do that product, all these are positive, and then the addition of positive non-negative numbers equals 0. That means every one of these numbers is 0. We will see. But remember, we want to show this, okay? Now let's go. If we have optimal solution, write it this way: x naught prime, and w naught. Okay? So we are assuming we have optimal solution in the problem, right? Because it says for any pair of optimal solutions. And this is the values of the slack variables, and the dual variables are from these optimal solutions. Now we keep going. Okay. At an optimal solution, this and this, we have from the duality theorem. Okay, from the duality theorem, it says the values of the optimal solution are the same. Now, where we got this from? We got this from here. I changed that here with this. So I got this here. So I got this equation now. Okay, in the dual problem, we have this. Why? Because W naught is a solution for the dual problem. So it must achieve that, right? Now, A transpose W naught is greater than C. Hence, what's happening here? We are saying we are taking this thing and replacing it with something like, okay, you see, this is greater than or equal, this is x naught transpose, but I will do here is replace A transpose with what? With C. Because we are saying A transpose W naught is greater than C. So I will write here C plus x naught prime transpose W naught. So I got this greater than that, which is this equation. Okay, now notice this number here is the same as this number here. So this number is greater than this number is greater than itself plus something. So that something must be what? Negative. When I say like a number z is greater than or equal z plus plus anything plus c plus t, for example, numbers. How this happens? This is because t is negative. How could this happen? So this takes the place of t. This is here and here is the same number. So we must conclude that to be negative in here. Okay, so this is x bar, x naught bar hat, x naught prime times w naught. And it is negative. How is that possible? The entries in these vectors, they are solutions. So the entries are all non-negative. So how come this to be greater or less than or equal 0? So we have this only choice. We cannot allow it to be negative. Cannot. Because this is multiplication of positive or non-negative. So, of non-negative, so the multiplication shall be non-negative, shall be 0. Oh, okay. So x naught prime w naught equals 0. But this equals, this is x naught prime w naught. And it equals 0. And each one of these is non-negative. So we must conclude that each one of these is 0. So we must conclude this equals to 0, this equals to 0, and this equals to 0, which means now xn plus I times wi equals to 0 for all I, and then we are done. This is what we wanted to show. So either this one is 0 or the other one is 0. Okay, again, let's see how we benefit from the above theorem. Consider the linear programming problem. The above theorem called the complementary slackness. So this is the primary problem, and these are the constraints. Then the dual problem is that. Now, remember at the beginning, introducing the theorem, we said when the equality is strict. When the equality is strict, that means the slack variable is positive, right? And so the corresponding dual variable is 0, because one of them has to be 0, right? Okay, now an optimal solution to this problem is x1 is 6, x2 is 0, and z is 12. Now look in here, x1 is 6 and x2 is 0, right? Okay, now if this is happening, then x1 is 6 and x2 is 0, and then this gets 6. So there is a slack variable. Pay attention to what I'm saying in here. If I substitute 6 in here and 0 in here, I don't get 8, I get 6. So we need to introduce a slack variable. Sorry, the slack variable we introduce here, which is x3, shall be 2, right? To make this equality, right? Because moving this to slack variable, it will become x1 plus 2x2 plus x3 equals 8, right? And we are saying that the optimal solution, this gives us the information. This is 0 and this is 6. So to make this equality true, then this slack variable has to take the value 3. That means, now remember that x3 is xn, which is 2 plus 1. Now this I, that means now w1 must be 0, because this is slack variable is positive. Now if you go here to the other one and make this introduce this with the slack variable, then we will have 3x1 plus 4x2 plus what? Now we will say this is x4 equals 18. Now we have for x1 to be 6 and x2 to be 0, and multiply, we get 18. So x4 must be 0. And x4 is xn plus 2. And so x2 must be 0. Okay? Okay. But we don't care about this now. We care about having x3 to be positive, which will force W1 to be 0. So in the optimal solution of the dual problem, which is W1, W2, they must have values for the optimal solution. Now we are confident that the value of W1 must be 0. W2 may be 0, maybe not. So this is what we are saying. Since there is a slack in the first constraint, the principle of complementary slackness says that the first dual variable must be 0 in the optimal solution of the dual problem. Thus, without evaluating the optimal function, we know the solution is that. And 12 must be the value of the dual of the objective function, because it must be equals to this. So we got a solution, and the first variable is 0. This is how we apply the complementary slackness. And we are done with today's lecture. Thank you.